Hey everyone, welcome to our presentation on our pseudo terminal project. We are Team 21, the Full Points Grade Association, FPGA. I'm Jack Locke.
I'm Ian Chadwick.
I'm John No.
And I am Sophia Delia.
Okay, this is the code overview portion of our project. We'll be going through the hierarchy of the pseudo terminal, which is mainly comprised of the input, the text input output commands and modules, and then the logic, which takes the commands from the text input output and uses it to control the various devices such as the VGA, the 7-segment displays, and the LEDs that are on the FPGA.
So I did the keyboard input, and it was one of the kind of interesting modules that we wrote because it utilized the PS2 input for serially transmitting data from a keyboard, and it's something that we hadn't really done yet before. So that was kind of interesting to learn about that. The module started off pretty complex, and it had 6 states and all kinds of different variables going on. And the way we tried to implement that originally was not giving us the correct output when it was linked up to the UART transmitter. So what I ended up doing was kind of stripping it down to the bare basics of what it really needed to do, so that way we could kind of troubleshoot it a little bit better, and then also make sure that it was delivering the results that we wanted. So what it does essentially, it takes in the PS2 clock, the onboard clock, the data stream, and it outputs a key code and a tick indicating that it's done, ready to be read by the UART. So if you will take a look at basically the main always block, reads in every negative edge of the PS2 clock and shifts it all the data bits into a register. And then finally at the end, it turns a flag on and off indicating that it's done. And then the way we originally had it set up was that it would send a done code after if the last code was a break code. The way the PS2 codes are sent from the keyboard, it's sent to key code, break code, key code, repeat. But what was happening was it was ending up repeating too many keys to the UART, and we were getting a lot of data streamed in. So what we ended up doing, I ended up rewriting it so that if the current code is a break code, it sends in the ASCII code, or sends output of the ASCII code of the last code read. And that ended up making it so that we could accurately read out the data keys one at a time.
All right, I'm Jack. I wrote the main code for the UART transmitter. The two main modules contained within this are the module that controls the baud rate counter that synchronizes, or excuse me, that tells the terminal that the UART is talking to the width of each pulse that's being sent. It basically takes the clock speed of the FPGA and divides it by the desired baud rate, which in this case is 9600, and it will count up to that value and send the bits one at a time from there. We also have some other functions built in to load things and clear things, but the shift of the register to the right is the main function that transmits the data. And then we have the state machine that really just alternates between idle and transmitting, and it stays in a steady 1 for its idle state, and then when it receives a 0 to drop low, that indicates that it starts a transmission of 1 byte of data. It will count 8 bits, and then it will send a final bit to indicate that the transmission is done. So 8 plus those 2 bits of the front end equal 10, and it will count those 10 bits and then revert back to idle mode. This is then also captured on the FPGA in a register, which is used. We have a concatenator that will take 5 of those values at a time. So it takes the 8-bit values and puts 5 of them into a 40-bit value. And that 40-bit value is then fed into the logic to execute our commands, which John will be talking about next.
Hi guys, so as Jack said, we're going to talk about the decoder next, which translates the 40 bits received from the concatenator into the logic module. First, the 40 bits are partitioned into 5 equal length wires called C1 to C5. Since the ALU performs 2-digit operations, the middle bit must be an operator, mathematical operator such as plus, minus, multiplication, X, or division. The first 2 partitions are also converted from ASCII to binary coded decimal, and then finally to binary values for use in the ALU. The outputs of the converters are only used if the range of ASCII characters falls within the numerical range, and if the command is an operator. Next, the command is sorted through various preset commands, and in each case, the module outputs an A value, a B value, an opcode, a go, and a reset value. So now we're going to talk about our core time module, which feeds into a stopwatch module, which is then used in our fight minigame. Firstly, the module takes in a clock, a reset, a start and stop, and outputs minutes, seconds, and hundredths of a second. In the always block here, we can see that if the reset button is pressed, then the 100-second parameter is set to 0. The register is set to 0. And if not, then the 100 seconds counts up to 359,999, which is the number of hundredths of a second in 1 hour. The output of that binary value is put into the core time decoder, which translates that into hundredths of a second, seconds, and minutes.
This is our graphics module, and it's the part of the VGA modules that actually draws designs on the screen. If you look starting at line 49 and ending at line 53, that is our counter that gives us a 25 megahertz clock. VGA displays have to run at 25 megahertz. And then starting at line 70, that is our case statement to choose what is output on the screen. For case 0, we output a blue screen. For case 1, we output a red screen. And for case 2, we output a green screen. And then starting at case 3 is when we start displaying the graphics for our mini games. So case 3 is a smile used in the fight mini game, and then case 4 is a pirate also used in the fight mini game. Case 5 is our last case, and that starts the disco screen. After you defeat the pirate successfully, a screen of multicolored squares displays to let you know that you won the game. The display signals module is the module that sets the scene for the graphics module. And then we generate our horizontal and vertical syncs. And then starting at line 70, we say, if you're at the edge of the 25 megahertz clock, if the X position equals the end of the screen, the X position returns back to 0. If the Y position equals the end of the screen, the Y position goes back to 0. Otherwise, it iterates downward 1. And then if the X position is not at the end of the screen, it generates forward 1 as well.
Hello, I'll be demonstrating the functionality of our FPGA pseudo terminal. So the setup we have here is the FPGA right in the middle. This is the keyboard where I'll be entering all the commands. On this monitor, you'll see the output of the VGA of the FPGA. And then in the bottom right-hand corner of this monitor is a PuTTY text terminal that will display the commands as we type them in. So I'll start by showing that we have full ASCII input to this terminal, and I'll type a quick sentence so you can see that. The lazy dog. And you can see on the FPGA itself that these 8 LEDs here show the ASCII value of the most recent character typed in. So those will be blinking as we go, showing which register is currently being pushed to the FPGA, which then gets sent to the terminal. So we have 5 functions on our FPGA: a calculator, a stopwatch, a greeting, a laser, and a fight. The laser and the fight are based off the fact that we had a midterm that involved a question with pirates. And so many of the things you'll see in this demonstration are pirate themed. I'll start with the calculator function. Now, every command we give the FPGA needs to be 5 letters long. And so as I type these commands, I'll be separating them with 5 spaces so you can more easily see them as we type across the terminal. The calculator takes 2 digits separated by a operator and then another 2 digits in the terminal, and then we'll display the result in the FPGA 7-segment displays. The functions it can perform are add, subtract, multiply, and divide, and I'll run through some of those for you. So first we'll start with 0, 3 plus 0, 5, which is 3 plus 5, and that should result in 8. All right, you can see 8 is displayed on the 7-segment display. Next, I'll show you 31 plus 27, which should result in 58. And that is indeed the case. All right, I'll do some subtraction functions. I'll start with 11 minus 7. 11 minus 7, which should result in 4. And you can see it results in 4. We can also accommodate negative values. So I'll do 23 minus 55, which should result in negative 32. And that is indeed the case. All right, for some multiplication functions, I'll do 3 times 4, resulting in 12. I'll do 0 times 12 to show that it can catch that. And of course it multiplies to 0. I will demonstrate one more just to show you some 2-digit outputs. 11 times 5, and that results in 55. Okay, and then finally we have division. I'll start with 30 divided by 5, which equals 6, remainder 0. And then I'll do, to demonstrate the remainder function on this end of the 7-segment display, 17 divided by 3, which should return 5, remainder 0. And indeed it does. And then just to show that it also catches edge cases, we have 56 divided by 0. And of course, we all know you can't divide 0 because that's bad, as it displays right there. Okay, next function that I'm going to display is the stopwatch. The stopwatch is actually used later in the fight game, but we decided to implement it as a separate module as well since we already built it. So I can go ahead and go to the 7-segment displays and type start. And the clock starts at 0 and keeps counting up. And then once I type in the word reset, it goes to 0 again. Next, we have greetings. We can type in any 5-letter greeting that you might have when you encounter somebody. So the idea was we come across a pirate, we can type hello. And the pirate will yell arg at us as it blinks. And then I'm going to switch to just a quick addition command to show that other greetings work as well. And let's type hey. And that brings us back to the response of the various greetings. And then finally, one other one we can do is pirate. And it displays arg again. Okay, the next module we implemented, part of our storyline was laser. So I'll go ahead and type laser. And what you'll see is a light show. And you can see those RGB LEDs transitioning.
Hey there, we're going to go ahead and demo the fight game for our FPGA project, the pseudo terminal. So it takes in 5 characters, and it's going to be fight, which starts it. So what happens is you have your friend who's slowly being overcome by piracy, and the time is not, once it turns full pirate, the stopwatch goes off, in which case you need to type STOP space, and it gives a little victory screen of our disco dance off with the pirate.